All right. Understanding the derivative and linear approximations. That is where we're at. So, there are times when we are interested in finding the effect of a small change. For example, how is the revenue at your local theater affected by a small change in the ticket prices for a movie? We could explore an application of the tangent line to a function called the linear approximation. You've already seen that a curve lies very close to its tangent line near the point of tangency. If you zoom in really repeatedly on a graph, the function will appear to be linear. When you have zoomed in to a sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish between the function and its tangent line. So think about what we did in 2-2, and we drew a tangent line, and it was close to the tangent line, and then the further away we got, the further the tangent line got from the curve, right? So local linearization is what we're talking about. So sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish between the function and its tangent line. This property of differential functions is commonly referred to local linearity. Yeah. So, in this first exploration, use a graphing utility to graph y equals sine of x. Well, we could do that. She's already done it there for us in a graph. But we could do it. We could go to our calculator and graph sine of x. We know that what it's going to basically look like, right? And it says zoom in at the origin 4 times. So zooming in, we could go to zoom in. There's 1 time. Zoom in. Really, there's 2 times. That's a pretty straight line, isn't it? Zoom in. That becomes really straight there, doesn't it? And if I zoom in a 4th time, it looks like a straight line, the identity function, doesn't it? Now, we know that it's not, but what we're looking at is that little piece right there, right? We're looking like from here to here. And yeah, that kind of looks like a straight line, doesn't it? Can you estimate the slope of the portion of the sine curve by inspection? What do you think that estimate of that slope would be about there? Of this line.
It looks like it's going down.
Yeah, that's what I would say. The slope appears to be about 1. What can you say about the slope of the tangent line at x equals 0 of the function y equals sine of x? Yeah, because if we were to look at this, and draw our tangent line here to that point, it's going to be pretty close to that, isn't it? So the slope of the tangent line at x equals 0 is about 1 on y equals sine of x. Write an equation of the tangent line for y equals sine of x at 0. Well, if x is 0, what is y? for when x is 0, what is y in sine of x? We know this right here. When x is 0, what is y? Right here? It's not 0, 0, isn't it? And we said our slope was also what? 0? Oh, no, you're right. Sorry. Not 1, but, or not 0, but 1. Yes? My brain and my mouth are not saying the same things. Okay, so then when we write our equation, we'd have y equals 1 times x minus 0 plus 0, which would really just be y equals, right, remember me saying it kind of looks like that identity function? Well, there you go. Questions there? Make sense? All right. Okay, function behavior related to the tangent line position. So, estimating derivatives of a function at a point. Sketch lines in each figure below. Use a straight edge to draw a tangent line beyond the point of tangency in each direction. So, looking at A, here we need to graph our line that is tangent to that point. It's going to be something like that, right?
Yeah.
Touches here. So the slope of the tangent line at point A. Let's estimate it. Well, let's see. We go up 1, 2, 3, 4, 5 over 1-ish. Do you agree?
Yeah, that's close.
I'd say about 5. Now, what about B? What's our tangent line going to be there?
It's straight 0.
It's going to be horizontal, so our slope would be, that's right. The slope of B would be 0. Slope at point B would be 0. And then C, let's see. My ruler kind of moved on me there.
It kind of looks like,
It's going to be negative for sure, isn't it? I don't know, maybe 2?
Yeah, maybe 2.
Something like that, negative 2? Something close to that at least, right? B is a little bit complicated because here we've always had smooth curves, haven't we? This one's at a point. So the slope of A is going to be pretty easy.
Yeah.
Because it's going to be that same exact line, isn't it? Like the tangent line at that, you can't really do anything besides draw a straight line there, can you?
Yeah, because you can't go through.
It can only touch, but the only way to touch is to draw the exact same pretty much line. Yes? So the slope of A, first of all, is going to be positive, and what's the slope of that line? The slope of A, first of all, is not going to be positive. It's going to be negative because it's going to the left, and it would be,
-2.
yeah. And the slope of C is pretty easy, and it would be,
+2.
yes. Now, B is where we've got a little bit complicated. Because here, as we're approaching those, it's at a sharp corner. It's not that nice line there. So you would kind of have a vertical tangent ish, or none at all. So that's what you're going to find, is that when you have a sharp corner, the slope of your you're not going to have a tangent line, so it will not exist. So it does not exist. So you can think of this as we approach B from the left, the slope was -2. As we approach B from the right, the slope was +2, correct? Okay, let's look at C. This one's also another interesting one. Let's look at A first. We can draw our tangent line. It is a curve, so that is a little bit easier to deal with. It's going to look something like this. I don't know, the slope of the tangent line at A, maybe negative. It's going to be negative for sure. Maybe 1/2. Something close to that. Do you agree? Somewhere around there. And then for C, pretty much going to be the same, except what? Yeah, it's positive. So the slope at C is going to be somewhere close to +1/2. Now, you can kind of think of this. The slope of this line is going down, 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 until it almost reaches vertical. And this one is going down, 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 almost until it reaches vertical, right? So you'd think of a vertical tangent line there. And the slope of a vertical tangent line, slope of any vertical line, does not exist. We'll look at D. If you look at that one, the slope of this line's going up until it reaches there. Slope of this line's going down until it reaches here. So what do you think? Our tangent line would be really a vertical line, wouldn't it? And the slope of a vertical line does not exist. So the position of the tangent line relative to the function it models depends on the concavity of the function at the point of tangency. Do we understand concavity? Concave down means it's kind of going in a downward motion, right? Concave up would then be from a going upward motion. So if we're looking at this function, at this point right here, it changes from concave down to concave up. Do you agree with that?
Oh.
So concave down, it's opening down, but then here it starts to open up. That's called a point of inflection.
You might shift your paper so you can see.
Oh, you can't see it, sorry. My bad. So concave down to concave up. So opening down, opening up, that's called your point of inflection. Okay? A little vocabulary there. All right. Throughout the course, you will be required to explain, justify, and defend your knowledge using proper terminology and precision. Use the graphs from example 2 above to complete the following statements. When the curve is concave up, the tangent line lies below the curve. So these were all concave down. Yeah, it was concave down. That's concave down. That's concave down. So if this is concave up, right? And you're talking about here, your point, your line of tangent would be here, so it's below the curve. Yes? Okay. When the curve is concave down, think of A, that is concave down. The tangent lines are all above the curve. A turning point, or a maximum and minimum, the tangent is, so think about this, the turning point. This is our maximum or minimum. The tangent slope is 0, correct? So the tangent is 0 or horizontal. So when you have maximums or minimums, your tangent will be 0. You'll have a horizontal tangent line. A point of inflection, where your concavity changes. So we talked about that, right? The point of inflection here. Where the concavity changes, the tangent is vertical, which does not exist, or 0, and we'll see another one like that here in a second. So here, if we have this, there, your vertical line would be there. Your tangent line would be there. Versus, think about the x cubed graph. Looks like that. This would be your point of inflection. Doesn't really change, but that would have a horizontal tangent line. At a sharp corner or cusp, the tangent does not exist. A point on a linear function, the tangent is the same slope. So think about this one. That was a linear function on either side, right? And so the same slope as the line. All right. Consider the radical function y equals the square root of x. Use the difference quotient to find the slope of the curve at x equals 9. So that means we're wanting the limit when it approaches 9. Do you agree? So we want the limit as x is approaching 9, and we're using the difference quotient. So the square root of x minus the square root of c, or 9 in this case, over x minus 9. Right? The function minus, yes, are we good? So here you have the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Now I can't do a direct substitution in there, so I've got to do some manipulation, don't I? What manipulation am I going to do? Rationalize the numerator. So I multiply the numerator and denominator by square root of x plus 3. So that gives me the limit as x approaches 9. Here, square root of x times square root of x is x minus 9 over x minus 9 times the square root of x plus 3. Well, those x plus 9 or minus 9s would cancel there, and we'd have the limit as x approaches 9 of 1 over the square root of x plus 3. And then we could actually substitute our 9 in and find that limit. So you'd have 1 over the square root of 9 plus 3. Square root of 9. I kind of have my square root over my 3, but it shouldn't be, should it? So that gives us 1 over 3 plus 3, or the derivative of the function at 9 would equal 1/3, 1/6. Wowzers. 3 plus 3 is 6.
Alright, now what's 2 plus 2?
Right? Yes? Does that make sense?
Yeah.
Okay. Write the equation for the linear approximation near 9. Well, we're still talking about the tangent line, essentially, because that's going to give us the linear approximation at that point, right? Now, we know the linear approximation at that point is not good for another point, but for that point, it's good. So here, we need to find our y-coordinate. To find our y-coordinate, we plug into the original function. So f of 9 would be the square root of 9, which is...
3.
So our point that we're talking about is 9, 3, and we have our slope right there, don't we?
Mm-hmm.
So it's just simply y equals 1/6 times x minus 9 plus 3. And if you were to multiply all that out, you would get that into slope-intercept form, right? It's the same thing that you've been doing since at least Algebra 1. It's just a different form, yeah? Okay, and it's actually an easier form, which is, like, it's easier to put it in there. You don't have as much work to get there. C, use the equation in B to estimate the value for 9.1. Don't use a calculator. So if we're estimating it, we'd have f of 9.1. It's going to be an approximation here. 1/6 times 9.1 minus 9 plus 3. Well, that would be 1.
It's square root of 9.1, right?
Yes, but you're plugging it in for this x value, right, where we had the square root of 9.
Yeah.
Do you understand what I'm getting? Like, yeah, you could just do the square root of 9.1 in your calculator. But to estimate it, we're just plugging 9.1 in for x.
Cool.
So here, this would give us, because this was our equation. Like, our original function's the square root of x, right? But our linear approximation for that at 9 was y equals 1/6 x minus 9 plus 3, right?
Okay.
So at x equals 9, these should be relatively close, yes?
Gotcha. Yep.
Does that make sense why we're using this to estimate it?
Mhm.
Okay. So this was 0.1 plus 3. Do you agree with that?
Yeah.
Now, I'm not super great at saying decimals and fractions, but I do know that this is 1/10 and this is 1/6, which when I multiply those would give me 1/60th. Yeah? So I know that this is going to be approximately 3.0 something, and I think it's like 1/6 something or other in there. So 1/60th I know would not be here, right? So do you understand why I'm saying it'd be 1/6-ish? Okay. So then D says graph the function and its tangent. Well, the original function is y equals the square root of x, yes? Well, y equals the square root of x. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. And it's going to be this nice, smooth curve. And then at 9, right? We want our tangent line. It's going to be something like this. Somewhere in there, right? Yeah? Touching but not crossing. And remember, our estimation was here when x was 9.1, so just a little bit past 9. We estimated on the linear approximation that it was about 3 and a little bit more. Well, look at that. Does that go on your line? And is it really close to that curve? Yeah. Explain whether your answer to C is an overestimate or an underestimate for the actual value. What do you think? Think about this. We're using this line, aren't we? Is that an over or an under? Over, right? So it's got to be an overestimate because the concavity there. Yes? So f of x is concave down. So the estimate is an over approximation because the tangent line lies above the function. Now find the true value of square root of 9.1. We would just plug that into our calculator, wouldn't we? So square root of 9.1, it tells us this is 3.01662, and it just keeps going. Well, my 3.016-ish, pretty stinking close to that.
Yeah.
I don't want to go too long, so. All right. Would your linear approximation formula be an accurate tool to estimate the square root of 25? Look up there. Do you think that line is going to estimate square root of 25 very well? Doesn't really estimate square root of 16 very well. And 25 is going to be more difference between the line and the curve, isn't there? So what do you think? Yeah, I would say no. No. And I would say the square root of 25 is too far away. From the point of tangency. And that means it's outside remember when we first started talking about this, it talked about a significantly small neighborhood and local. So I'd say it's outside the local neighborhood. I'm going to put that in quotes there. Something around, something like that, right? It doesn't have to be my words. It can be your words. Make sense, though? Okay. Now, we are going to use the graph of the continuous function y equals g of x shown to complete the table. We know that the derivative of a function at a point represents the slope of the tangent line at that point, right? Estimate the value of the derivative of g of x for each x value in the table by drawing a tangent line through the given point of tangency. Then estimate the slope, which is the derivative, at that point. Find the y-coordinate of the point of tangencies and use the point-slope form of an equation to write an equation of the tangent line at the point x equals a for each x value. So first of all, at -3, 1, 2, 3, we're talking about point A, correct? Which is -3, -3. Do you agree? That's the point. So then we have to draw our tangent line. So somewhere around in there. I didn't get my ruler as close to the point as I would have liked. So to estimate our derivative, we're going to estimate that slope, right? Well, I'd count up 3, 4, 5, maybe 6 over 1. I don't know. Yeah, 6 over 1, something like that. But it's -6 over 1. So look at the original function. Is it increasing or decreasing? What's the behavior of that function right there? We always look from left to right, don't we? So the original function is going down at A, isn't it? So it is decreasing. Do you agree with that? Now to write our equation, you just simply have y equals, our slope was -6, times x minus x would end up being +3, and then plus y would end up being -3. Yeah? Mm-hmm. All right, -2, when x is -2, we're talking about point B, -2, 1, 2, 3, 4, 5, 6. That would be our point of tangency, yes? Yeah. So that would be -2, -6. Now, that's a curve and a minimum, isn't it? Yeah? And so we know our tangent line would be a horizontal line. Do you agree with that? Good. And so what's the slope of a horizontal line?
0.
And what's the behavior? Is it increasing or decreasing?
No.
No, it's constant, isn't it?
Yeah.
Now, to graph this line, yeah, you could use this and you could say it's y equals 0 times x plus 2 minus 6, but what is that really going to end up just being?
Y equals -6.
Yeah. Okay, at -1/2. So at -1/2, we're down, what, 1, 2? That's point C. So at -1/2, we're down 2. So we're still concave up, aren't we? So our tangent line is still going to be above the curve. It's going to be really close to what? Let's see. 1, 2, that's about 3/1, isn't it? Because that's about at 1/2, and that was at 1/2. About 3/1. So I would call the slope 3 there. And is that original function increasing or decreasing or constant there?
It is increasing.
Yeah, it's increasing. And so our equation would be y equals 3 times x plus 1/2 minus 2. This says 1.25. So if we go right 1 and a little bit more, we're up here at D, which is where at 1 maybe? Kind of looks like 1 to me.
It's just to the right of 1.
I'm going to call it, well, yes, this is right of 1, that's 1.25, but it's up at 1, isn't it?
Yes.
So 1.25, and that would be up at 1. That would be our point. And what about that tangent line? What is it going to be? Horizontal, right? It's horizontal because it's a relative maximum there, isn't it? So that slope would be 0. It would be constant. And our equation would just end up being y equals 1. All right, and then it says to go right 4. So at x is 4, 1, 2, 3, 4. We're talking about point G. So 1, 2, 3. So you're at the point 4, 3. Now this is concave up. Concave up. Your slope here, I might need to extend that further because it's not going very far. I didn't do a very good job of drawing that. Let's see, we go down 1, 2, 3, 4, 5, 6/1 about, maybe, something like that.
Yeah.
6 or 7 even, maybe. I don't know, that might be even more close. Somewhere around there, 6 or 7, yes. It's not going to be exact. But that function is increasing, isn't it?
Yes.
And so our equation would be y equals 7 times x minus 4 and plus 3. And we will finish this next time.